So my method finally ranked just under the 21% mark. And I'm going to, a bit as Lucas explained, that you can rank in the top 10, even top 3 with simple linear regression techniques. And then I'm going to slightly improve this using a neural network. So, well, this is just about handling the missing values in the raw data. So I recorded the number of missing stocks on individual dates in a feature, and the number of missing volatilities in the time series in features as well. And I just replaced missing returns by zeros. So here we have a typical volatility intraday. So baseline estimator I used was the mean of the volatility starting after a certain timestamp here. So that's been optimized by cross-validation. So that was like the median or something else, kind of a good baseline estimator. So as we are predicting a low frequency value on average in the afternoon, I used low frequency indicators. So I used the moving average, like yielding like 6 values here, or a bit more if I use overlapping between the windows. I tried to do parabolic fits of the stock volatility because we observed a very strong intraday seasonality, a U shape, but that didn't, or wavelet decomposition. Well, there was a module for doing that, so that didn't turn out really well. I mean, no great improvement. I was also very disappointed in the returns, as you were. They had a very low predictive values. I tried a number of things, estimating prices with these returns on the volatilities, like very approximate estimate, trying to use them as weights for the volatilities. As I read some articles that use that. Well, I finally only used the variance of the returns towards the end as a relevant feature. That's what I found out. So now let us acknowledge the market. So as Lucas, I calculated the correlation matrix here between the stocks so that we could evolve from a naive view of the market as just being the average of the volatilities to a stock-specific feature that used these correlations as weights. So here you can see that the stocks are very well correlated together, stock-to-stock correlation, and you can see that indeed you have, depending on the stock, a stronger or not correlation to the market. So now we have to acknowledge the stock number represented by this integer. So same remarks, that's a categorical feature with many values. So you can implement it by using one regressor per stock, but then you have less data points, 2,000 dates. Or you could use one-hot encoding, but then you have an explosion of the feature space. Or you could use clustering, which you did. I didn't use it at this point, but as I will say later, with the embedding technique, I have kind of a continuous clustering technique. So finally, here's the result for the linear regression. So I used, as you did, one regressor per stock. So these are my features. Well, 15 features for one stock. So normalize and then feed them in. So I first do a fit with ordinary squares with the same weights as you used. But then I used a minimizer. You know, they come packaged. And I just minimized the MAP error function. So I got the real optimized MAP solution. This didn't bring a great improvement over the first technique, but it's comforting. And if I came across negative predictions, I would turn them to 0. So this I ranked a bit less than you did with this technique, I guess because I didn't use any clustering in the final approach. But we can see it's very close from the best score of serial. Well, that's just the feature correlation map. So the remarks I can come up with is that linear models perform well, so we expect quasi-linear models to perform even better. So stacking linear models, that's your solution, if I can understand well. That's the solution that's been used by Mr. Garcia as well, stacking Huber regressors, quasi-linear regressors. And if you use neural networks with ReLU activations and early stopping, then you have as well a quasi-linear regressor. And you expect tree-based or highly nonlinear models not to perform well because a tree is not the best tool to fit a line. And indeed, the XBoost trees didn't work well with this data. So, the conclusion here is that advanced machine learning techniques do not seem to bring great progress to this particular problem. So maybe if we had more complete data, like not just the sign of the returns, but the complete values of the returns, or more information about the definition of the volatility, well, maybe we could really outperform linear regression. So let me present to you my neural net. So that's the architecture of the net. I will start by the end. So we have a very classical multi-layered perceptron here, with one hidden layer, 20 neurons, 5 neurons on the linear output neuron. And we input 26 features here. So we retain kind of the same features as for the linear regression here, but we take in account the stock number in a different way, which I will explain later, using embedding features. So here we have 4 embedded features with a dense layer. And the market as well is not represented using the correlation matrix, but the correlations are learned by the net. So here we have a dense layer with L2 regularization that is fed with the different averages of the stocks, and that outputs 5 market features. And actually also fed with the embedded features here. So that's very practical with the Keras API. You can actually have inputs and outputs in a very transparent way. So what about these embedded features? So the idea is that as the stocks are highly correlated, then the information that you have about one stock should be relevant for another stock that's very correlated to this one. So instead of treating them in an orthogonal way, with one hot encoding or different regressors, then the idea is to project this 318 discrete stock value space into a much smaller continuous vector space, used for. So you achieve dimensionality reduction, so you can avoid overfitting and accelerate training. And the similar stocks will be projected to neighboring points in this new space. So it's kind of a continuous clustering. You can see that. You can see this technique like that. This is actually a very common way of doing things in natural language processing. So here we have an example. If you have a vocabulary of 36 words and an output dimension of 2, then after training, you can see that words with a close semantic value are grouped in the same region of the space. So I applied that to the stock number. So here you have, for the demonstration, I just used the n equal 1 here, so just one output feature, one output embedded feature. So the vocabulary size is 318 here. And this is the initial uniform random distribution. So that's the embedded feature. One point is one stock. And you have here the mean target for each stock. So you can see it's random. Then after training, so I trained the network using only this embedded feature as input. You can achieve an MPA of 38%. And you can see now that stocks have the embedded feature now reflects the average target for each stock. And you can see, for example, that illiquid stocks are clustered together. So I used this model, and I use bagging, so I use an average of 5 of these models with a five-fold cross-validation. So here's the result. You have the predicted values against the targets here. That's typical evolution of the training error and the validation error. Well, depending on the training and validation sets, this can be higher or lower. And so, so it's been, so the training speed was 2 minutes per epoch. So that was 5 hours per average model. That's on a 10-year-old CPU, so there was only a very rough optimization that has been conducted actually on this number of layers, number of neurons, and all that. Well, I made a few other attempts in order to get nicer features. The first one using convolution 1D in order to have an optimal filtering of the time series data. And the second one using a recurrent net, LSTM and GRUs, but that didn't work so well for me, so I think Cyril will give a better understanding of these things later. Here we go. So there was some frustration with the partial information of the data and using the returns. But we can see that carefully selected engineered features, well, still perform quite well. And overall, it's been a great opportunity to practice data science. Thank you.